Hello and welcome to another video. In this video we're going to be going over the problems from Weekly Contest 408. And so let's get started. So in the first one, you're given a array of positive integers nums, and you have a game where Alice can pick all single-digit numbers or double-digit numbers, and the rest are given to Bob. And Alice wins if the sum of her pick is greater than Bob's. So return true if Alice can win the game. So basically, all you have to do for this one is you can just calculate the sum of all the single and double digit numbers. So all the single digit numbers are less than 10, and all the double digit numbers are greater than 10. And Alice wins if they're not the same. So I just did a small simplification where if the number was single digit, I added it, and if it was double digit, I subtracted. And then if those totals are exactly the same, then your cumulative total will be 0. So if it's not 0, then just basically Alice wins by picking the bigger one. So the only way Alice loses is if they're exactly the same. So pretty easy there. Okay. This one, so you're given two positive integers L and R, and for any number x, all positive divisors of x are called proper divisors of x. A number is called special if it has two proper divisors. So 4 is special because it has proper divisors 1 and 2, 6 is not, and so on. So from 5 to 7 there aren't any, from 4 to 16 there's 4 and 9. And so basically, in order for a number to be here, it needs to be divisible by 1 and, let's see actually, so yeah, so it needs to be divisible by two different numbers, not counting itself, right? And the only way for that to happen, so basically it needs to be divisible by 1 and itself, and one more number. So if you think about it, if a number has factors, and the factors are 1 itself and only one more, that means it has to be the square of a prime number. Because if it has two other factors that are different, it's not going to work. And if that, if it's a square of a number that's not prime, like let's say we have 36, it's a square of 6. So 6 can be broken down into something else, like 3 and 2, and then you can get 2 times whatever the other thing you need to get that number. It's if it's like 6 times 6, if you can break down one of these into like 3 and 2, then we can just say like, well, we can just do 3 times 12 or like 2 times, other stuff. So basically you're looking for numbers that are squares of a prime number. And these constraints are pretty big, so you can't just like go through every number and check. So instead, what we can do is we can just take every prime number, or actually every number up to the square root of r. And you can make this like a little bit more faster, but the time complexity will be the same. So let's say r is like 10 to the 9th or whatever it is. We can check every number up to square root of 10 to the 9th. And for all of those, we can just check, is it prime? And if it's prime and it's between L and R, then it's going to be valid. So like in this case, the square root of 7 is 2, so at the upper bound will be square root of 2. So we can check like 0, 1, and 2. So 0 and 1 aren't prime, and 2 would work. 2 isn't prime, but 2 would work as a square root, because 2 squared would be 4, and 4 is one of these special numbers, but 0 and 1 aren't. So in this case, you would say like 0 isn't, 1 is not, and 2 is, and 2 squared is not in this range. So there's none for this, but here, the square root of 16 is 4, so you would do like 0, 1, 2, 3, 4. So 0, 1 are not. 2 squared is, and 2 squared is in here, and then 3 squared is, and 4 is not prime, so it wouldn't be in here. So basically, you just take every single number that's less than the square root of this guy, and you just check, is it prime? And if it's prime and it's within that range, that's one of your answers. And there's like a shortcut way to do this called the sieve of or something, can never pronounce it, sieve of Aristophanes or Stephanes or whatever it is. And basically, if you have a range of numbers and you're trying to figure out if it's prime, so if you have just distinct numbers, you can just do like a basic check all the factors in the range of 1 to square root of that number. But if you have a range like 1 to n, which in this case we do, right, or 0 to n, there's a way to do it faster than that. So basically, if I have a bunch of numbers like, so we're not going to do 0 and 1, we're just going to do 2 upwards. So if I have a range like 2, 3, 4, 5, 6, 7, 8, 9, 10, let's say, these are my numbers and I'm trying to figure out which ones are prime. So if I have a range without missing anything, basically what you do is first you say they're all prime. Then you go through them, and for every number that is prime, multiples of that number can't be prime. So you basically say like, okay, 2 is prime. So then let me go through all of multiples of 2 and mark those as not prime. So basically it would be like 2 true, 3, let's say these are all true for in the beginning. You'd say like, okay, 2 is prime, fine. Let me go through all multiples of 2 in this range. So I'm going to go through 4, I'm going to mark it false, 6, false, 8, false, 10, false. Then I'm going to go to the next number. So 3 is true, that means all multiples of 3 are going to be marked false. So 6 is false and 9 is false. Then 4 is not a prime, so I can skip it. 5, it says it is a prime, so I need to mark 5 and 10 false. 6 is not, 7 is, 8 is not, or 7 is, but there's no other numbers in the range, and these are all not. So you can basically get all the primes like this quickly. So the primes here would be 2, 3, 5, and 7. Technically true, 2 is not prime, but for the case of this thing it is. So that's how you do it quickly, and this will basically be n log n, I believe, because for every number that's prime, you're going to go through your whole loop. And so for a number to go through the whole loop, that's log n. It'll be log of like different base. So if it's 2, it'll be like log base 2 of n. If it's 3, it'll be log base 3 of n, 4, and so on. But basically that whole thing takes n log base 2 of n, or just n log n. And because we're going through the numbers 1 through square root of r, it's like, it ends up being like square root of r times log square root of r or something like that, which is fine. You can also speed this up. So once you get the range of numbers you're looking for, you can get the exact range. I just did 0 to the top bound. You can only look through numbers in between here. You can also binary search for like the first number that's in here and the last number that's in here. But all that is just small things. It's basically going to be the same thing. So like I said, you just go through every prime number or every number that's less than the square root of this guy or less than or equal to, and then you check, is it prime or not? If it is, then you have one more of these. So you can definitely make it a little bit more efficient if you want, but this works. And yeah, you can look up that sieve of, oops, go back, let me go to here. I might have had it pulled up, let's see. Yes, it's called Eratosthenes, and I've used it before. And yeah, you can basically Google that if you want to. Or you could just do the normal prime number, either one. That one's just a little bit faster. Okay. So this one, and these last two are pretty tough. This one's pretty tough as well. This I got terrible runtime. I think you could do it better, but it did pass. And also, crazy thing is this has like no acceptance, which is pretty insane. And also, when I was looking at the contest, I think this problem took people longer than the last problem, and the last problem was kind of screwed up. So this one, you're given a binary string of s, and you want to return the number of substrings with dominant ones. A string has dominant ones if the number of ones is greater than or equal to the square of the number of zeros. So in this case, they show you like what are all the strings. So for example, 1 would be a string, this one would be a string, this would be a string, this would be a string, and this would be a string, something like that. So it's 5 total. And then here there's a bunch that are, and then there's some that aren't. So the basic idea you need to solve this problem is, so if a string is length, some length, right, length s, because you need to have ones be greater than or equal to the square of zeros, that means that the upper bound for the number of zeros you can have is roughly square root of the string. Because if the string is like 100 and I have more than you know, even if I can't even have 10, right? Because if I have 10 zeros, I would need to have 100 ones for that to be valid. So the upper bound is somewhere around the square root. So what we can do is we can just check for all strings. So we can say like, okay, well, if the string, like, let's see, string length is 10 to the 4th here. So we can just say like, let's just count all strings with number of zeros from 0 to square root of the length of the string. And so we can basically, for each one of these situations, so we'll just say like, let's try 0 zeros, let's try 1 0, let's try 2 zeros, let's try 3 zeros, let's try 4, and that's fine. And then for each one of those, we'll do a sliding window. So that's going to be like square root of n times n, which will pass. Yeah, because square root of this guy is like 10 squared or something. So it barely passes, but it passes. And so then the idea is basically given a string. So let's look at this guy. Let's say we're looking for all strings with 0 zeros. Yeah, so that sliding window is pretty straightforward. And then like this would be a string, and then like this would be a string, and then this would be a string, and then basically everything with 0 zeros would be a string. And then as you grow your string, so let's say like this was a string, and then you add this on, how many new strings do we have? So we basically, anytime we add a thing, the number of new strings we have is just the length of our entire string. So when we had something like this and we add this, we add 2 new strings, because we can have this guy or this guy. If we had these two and we add another one, we add three new ones. If we had this, we add 4, and so on. So with no zeros, it's pretty easy. But what about if we do have some zeros? Like if we have some substring that's like the biggest one we can have, how many substrings does that create? So for example, let's say we're looking for all substrings with 1 0. So let's say we have this in our sliding window, and then we add this. How many did we add here? So if we add this, we actually added 2 substrings, because we can have this one or this one. And how do we figure that out? So basically our window will be the biggest string possible containing 1 0, like as you go. And then the other thing you need to keep track of is the smallest string possible containing 1 0. So the biggest is this, the smallest is this, and then that difference is how many you have. So here, like we'll have a pointer here, and we'll have a pointer here. Similarly, if we have this and we add this, how many did we add? Well, our smallest window would be here, and our biggest window would be here. So the difference there is 2. So there's 3 different indices you can have. So you can have here, here, or here. So you would have 3 different substrings, right? This guy would be 1, this would be 1, and this would be 1. And basically, I use a deck, but you can use a 3-pointer sliding window. I did that before. So the basic idea is we're going to try to look at all the substrings with all the different amounts of zeros we can have, and that range is the square root of s. So we're going to have our sliding window, we'll have the number of zeros, number of ones, and then I created a location, which is just the location of every single 0 in the window. You can probably optimize this a bit, but it doesn't really matter. And then I also created how many, like what's the square of this guy. And so if it's a 0, we add a 0, and we add the location to our queue. If it's a 1, we add a 1. If we have more zeros than what we want, we're going to keep removing zeros. And if we removed a 0 that was in our queue, we're going to remove it from our queue. So our queue, like let's say we have like this example here, and we have this last part of the string, our queue will just have the location of this 0, which is like at index 1, 2, 3, 4. So this will be a 4. And then we know all we need to know is the location of the first 0 in our substring, because that's the one we can't get rid of. Like we have to have exactly this many. So we have the location of this guy, we have the location of the left, and the difference is how many different, close this, how many different strings this new thing adds. So basically, as your zeros, yeah, as your zeros is greater than I, you want to shrink. And if one of your locations is no longer in your sliding window, you just get rid of it. And then we just check here. So if we have exactly what we want, and the number of ones is greater than or equal to the square of the zeros, if we don't have any zeros, that means the number of substrings or new string added, right? This is this case, is just the length of this whole thing. So right below itself plus 1. Otherwise, so here's the other thing. So there's another thing to consider. So let's say we have like, let's say we're looking for substrings with 2 zeros, and this is one that we find. Yeah, so let's say this is our current sliding window. So yes, this is our first location of a 0, and this is our left, but we can't get rid of, we can only get rid of so many 1s. So we can figure out like, okay, this is our location of a 0, but how many 1s can we get rid of to keep this valid? And the ones we can get rid of, so we can calculate the difference of 1s and 0s. So here, 1s is 4, and 0 squared is 4. So we actually can't get rid of any 1s, which means we only have one valid window. So we basically figure out like how many 1s can we get rid of, and then where the location of the 0 is. And everything before the 0 is all 1s. It has to be all 1s. And then this is what I did here. So the number of 1s we can get rid of is here. It's just how many more 1s do we have than the squared zeros. And then this is the location of the 0. So we can't get rid of a 0, but we also can't get rid of any more 1s than, like, we can't get rid of 1s to make the 1s, like if this is false, then we can't do that either, right? So we can just calculate it here, and the minimum of those is how many substrings we add. So hopefully that makes sense. Kind of confusing, definitely super bad acceptance rate, so kind of happy I got this one. And yeah, it barely passed, so. Yeah, I think this is the lowest acceptance rate I've seen, so I'm not sure what's going on here, to be honest. Like, there's problems that took me like hours that had like 20% acceptance, and this one was like less than an hour. So no idea. Yeah, and it literally barely passes, so. You can optimize some stuff, but yeah. Okay. Yeah, for these contests, I'm mostly just trying to get the problems done, not super concerned with like maximum efficiency, because these get pretty hard. Okay, so here, last one. You're given x and y and circles, where circles are x and y and a radius. And there's a rectangle. Let me just. So here we have a rectangle with an x and y coordinate here, and we have a bunch of circles. And we're basically asked, given a bunch of circles, can we get from here to here without, I think there's some rules here, so let's see. Yeah, so you can't touch any circle or touch the rectangle on a side. So you need a path where you go from here to here, and you can't touch a circle, and you can't touch any sides of a rectangle. And they basically ask you just, is this possible or not? Also this, I think in this one, like I was looking at some solutions, and I think in this one, the description is like wrong, because there is like this, technically there is a path, but this says no. Like in this actual problem, if you put this in, it'll say there is no path, even though there is. So basically, we have to assume for this problem is all the centers of the circles are inside your rectangle. So you can't have circles like this, because this would make it more complicated. So they didn't write that, but basically I think you just have to assume that all the centers of your circles are inside the rectangle, and then you can't have a case like this. So in this case, you can get there. In this case, you can't, because the star is already in a circle. And in this one, you can't. Kind of hard to see, but there is actually 2 circles here, so there's no way to go around, because the circle touches this side, the circle touches this side, so there's no way to get through. Okay, and I was drawing some stuff here, so let's take this example. So let's say this is our like rectangle. I wonder if I can draw a line. Okay, so let's say this is our rectangle, and I think, there we go. So we're trying to go from here to here. So if you look, here's a bunch of circles, and you actually can't get here. You can't go from here to here because this wall is occupied and this wall is occupied, or this wall doesn't matter because you can go around. This wall is occupied. So basically, let's just say we have one circle to make this easier. I wonder if I can reset this thing. Yeah, okay. So let's say we're just trying to get to, okay, don't want that. I wonder if I can move it. Nope. Okay, so let's say we're trying to get like over here and we have one circle. So actually it's probably just easier drawing here. So let's say we're trying to get like from here to here and we have one circle. So one circle, depending on how it is, so if your circle touches, let's label these. Let's say this is the left. Let's say this is the right. This is top, bottom. Okay, and like I said, we're going to assume all the centers of the circles are inside the rectangle. Otherwise, you're going to have some weird stuff that should pass but fails in here because I think they just didn't write that, but they assumed that in the problem. So if we have a circle, and the circle touches the left and the bottom in any way, no matter how you put the circle, you're never going to be able to get through. So like this or like this, it doesn't matter. If it touches the left and the bottom, you can't get through. So left and bottom, fail, no matter how. Also, if it touches the top and the right in any way, you will never be able to get through. So same thing. And then there's two more. If it touches the top and the bottom in any way, like, let's just say, obviously it's not a circle, but whatever. Those will be fine. Like, let's say a rectangle is like this, this, and our circle, actually now let's draw it the other way. So let's say our rectangle is like this. There we go. And our circle is a circle like this. So if it touches the top and the bottom, you can never get through. So yeah, so I said top and bottom. Left and right, same thing. I think I missed one of them, but yeah. So left and right, let's say a rectangle is like this. And our circle touches the left and the right, then we're not going to be able to get through either, even if it doesn't touch the top or the bottom. So left plus right. And then the last one was top and right. I think I wrote that before earlier. So basically, if we have one circle, if it touches two of these points, the only one it's allowed to touch, so it can touch the left and the top, and it can still be fine. So like this can still pass because we can just still get through here, right? So like here's a path. And then it can also touch the right and the bottom. Same thing. But if it touches any two of these, it'll always fail. Okay, so now let's say we have two circles. And let's say one circle touches the left. Let's say the circles are also connected. And the other circle touches the bottom. So, yeah. Whoops, not that. Where is it? Okay, I think I can, okay. Let's do this, there we go. So let's say, I don't know, whatever. Yeah, that's annoying. So let's say we have these two circles. So one touches the bottom, one touches the left. So if circles are connected and you can basically treat them as one circle. So if one touches the bottom and one touches the left, that's the same thing as one circle touching the left. Also, if you have a bunch, it's the same thing, right? If you have like these two are connected and then like this one's connected to this or, you know, something like that. So basically, if you have a group of circles that are connected, if any one in the group touches the left and the bottom, you fail. If any one in the group, or not any one of the group, if any one of the whole group combined touches like any one of these, like, so as long as this whole group touches these, you can never get through. Same thing with top and bottom. Same thing with top and right, and all that. So these are the cases you're looking for to fail. So basically what you can do, because you only have 1,000 circles, you can, first of all, for every circle, you can check what things it touches. So for every circle, you can say like, does it touch the top? Does it touch the bottom? Does it touch the left? Does it touch the right? And that's pretty easy. You just get its center point. So like, let's say it's at like, let me go back to this coordinate plane. So let's say a circle is like here. You can actually do this. So I don't know why I can't get rid of that. Let me see if I can reset it. Okay, so I can just say like I have a circle here with a radius. So if I have a circle here and my radius, not that one actually. I think it lets you do, here we go. So you can say like if my center is here and my radius is like 3, then I know that like if my center is here, the leftmost it goes on the x-axis is where it starts minus the radius. The rightmost is where it starts plus the radius. The top is where it starts plus the radius, and so on and so on. So if this is at 5, 4, that means left, and the radius of 3, that means left it'll go to 2, right it'll go to 8, and the y-axis same thing. So up it'll go to 7, and so on. And so you can basically figure out like where it'll go, where's your rectangle, and then where it touches, right? So let's say the rectangle happened to be here. Yeah, let's say like this is our point up here, so 9, 7, you could say like, well, it goes enough to touch the top, it doesn't touch the right, it doesn't touch the bottom, it doesn't touch the left. So you can do this for every single circle, and you'll just have like this array of 4 things, of 4 corners it touches. Then whenever you combine circles, you can just take every circle and every other circle, and if they overlap, you can combine the things they touch. So like, let's say we have one circle that touches like this, and then another circle. Obviously this isn't going to be a circle, but let's pretend they are. So one touches the top, one touches the bottom. So we'll combine them into one like group, and now we'll say that they touch the top and the bottom, and somehow, and not the left and not the right. And so basically what you can do is you can just do a union find here. So let's look at the code. So we have the standard union find, and then all we add is this other thing. And this paths is basically, I don't know if this is the best name, but this is basically the corners of the rectangle it touches. So we have 4 paths, so it'll be like left, right, top, and bottom. And we have this for every single circle. So the node in the union find is a circle. And then whenever you combine circles, you just say like, okay, what's the new parent? And when I combine 2 nodes, I'm going to say, I'm going to take all the things that one circle touched, all the things the other circle touched, and the combination will be, if any one of those 2 circles touched it, then that will be true. So here we have it here. So like if x is the new parent, we're going to say if x touched it or if y touched it, this will be touched in this path. Like I said, path probably not the best name. So basically just a union find with this little addition of an array of 4 things that you intersect with. Maybe intersections might be better or something. So we make a union find, and then for every circle, we check what it touches, left, right, top, or bottom. Then, for every single group of circles that aren't the same, we check how far apart. Oh, by the way, so the other thing is, for 2 circles, how do you figure out if they connect, right? So that part's pretty easy. So if you have 2 circles, like let's say you have one here, let's say you have one here, the radius of 2 or something. Basically, you can calculate this distance. So distance between 2 points is just the square root of the, so it's this equation here, square root of x2 minus x1 squared plus y2 minus y1 squared, right? Because like you have some thing, let's say they aren't on exactly the same thing here. So let's say maybe here. So the distance would be here. And the reason it's what I said is because, because you can basically make a right triangle here, right? So this is just like the hypotenuse of a right triangle. So it's like this and this. Hopefully, I haven't used this before, so I was just trying it out. So like this distance is just, this is the height, this is the width, or this is like one side, the other side, a right triangle, and this length is just the Pythagorean theorem. So that's why you can do that. So you get this distance, and then you figure out, like, in order to figure out if they touch, you figure out like what's the radius of one and what's the radius of the other. And so if the radius of one and the other, so if this distance is less than or equal to radius of one plus radius of the other, that means these circles overlap, right? Because the circle goes out radius and then the circle goes out radius. So that's why. So that's what I did here. So this is this distance, and then if the distance is less than the radius total, then these circles overlap, so you do a union. And then we check, after we did all the unions, we just check all of our groups now. And all we have to do is just check for these cases. So 0 and 3, I wrote it down, is left and bottom, right? So if left and bottom are both touched, you can't go across. If right and top, you can't go across. And then if 0 and 1 is left and right, you can't go across, and then top and bottom, you can't go across. So if you ever have any one of these for any group of circles, you can't go across. Otherwise, you just return true. So hopefully that makes sense, and you can redo this problem and just tell yourself the other constraint that these circles are, the radius of all these circles are in the rectangle. They don't tell you that, but basically, like I said, this should fail, but this should say there is a path. But if you put in this, it'll say no path in this problem. So yeah, because if you count these things, there's like a bunch of other cases that we haven't looked into, and that would make the problem more complicated. But I think whoever wrote it just like made a mistake or something. Yeah, so this one also takes a while, but yeah. So it's not too bad, just some basic like algebra stuff. I will say I think this one's harder, barely passed, maybe. I mean, it should pass, right, I guess, or close. I guess it would be, I think there's a way to do this in like linear time. Yeah, n square root is what I did. Oh no, I guess people did the same thing, n square root of n. So maybe there isn't a no of n, I don't know. Yeah, not sure. So I guess people did do this thing as well. I thought there was a way to do it in like linear time, but I don't see it, so yeah, I don't know. I guess maybe it just does take a long time. Okay, so let's go through the runtimes of all this stuff. So this union find. So here, for every circle, we put in the union find. So that's O of circles. Here, so I think this is just circle squared. And this is O of circles, because we have the union find. Okay. This one is n square root of n, and space is O of n, because we have a deck. You don't need the deck. You can definitely use more pointers to make it O of 1 if you want to. It was hard enough, I think, so, and I was just trying to get these done. So instead of the deck, you can use the closest and the farthest. I think the 3-pointer sliding window would work here too. That might, yeah. So here, so we have the square root of the right side. So maybe like square root of n. And then for each one of those, we do that sieve thing. So that's like square root of n log square root of n or something like that. That's what it ends up being total. And space is O of square root of n. Yeah. Because we go from 0 to square root of n. And then here, this is just linear. All right, and that's going to be all. So hopefully it was helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.